So we've talked previously about the Hertzsprung-Russell diagram, this graph where we have the luminosity of different stars on the vertical axis, the spectral type going from the hottest surface temperature, the highest surface temperature, O, to the lowest surface temperature, M, this OBAFGKM classification scheme. And we saw that there are different luminosity classes of stars, the main sequence, the giants and supergiants, and the white dwarfs. And specifically along the main sequence, we saw some properties of how if you are on this main sequence band, the stars that are higher up and to the left of this diagram have higher masses, higher core temps and fusion rates, and shorter main sequence lifetimes. Whereas on the lower end, we have low core temps, low fusion rates, low mass, and longer lifetimes. We want to have a way of actually testing these particular claims. I mentioned how we do use computer simulations to try to model the interior of stars, to try to predict how long they would last. But we also would really like to have some observational evidence to talk about this. And this is where star clusters come in very handy. When we talk about star formation, we're going to find that stars generally don't form just on their own. You don't have just one star forming out of one cloud of dust and gas in space. What you have is a giant cloud of dust and gas in space, and as it collapses, it will form an entire cluster of stars containing, possibly in the many thousands to, in some cases, over 1 million individual stars from one giant molecular cloud. And these stars that are forming, they have a wide range of masses. So when we talk about star formation in some of the next sessions, we're going to talk about how more of the stars that form are going to be low mass main sequence stars, but we're still going to get a few high mass main sequence stars. We get a fairly wide range of star masses produced in this single cluster at approximately the same time. What this means is these star clusters give us a way of looking at, if all of these stars are the same age, how have different massed stars in the sample aged differently over the same period of time? Okay? So each star cluster basically gives us a different snapshot of stellar evolution, and we can draw these Hertzsprung-Russell-like diagrams. Usually that will be, instead of just luminosity, it will be apparent brightness on the vertical axis and spectral type on the horizontal axis. So for example, this image shows a relatively young cluster. We see a few of these very high mass, very high temperature blue main sequence stars. And most of the other ones would be the low mass main sequence stars. But if we look at this diagram, let's say we look at the luminosity versus the surface temperature. And this red line represents the main sequence stars, that main sequence band. And most of those stars are, in fact, main sequence stars. The fact that even these high mass, even though there are some high mass main sequence stars there, means that this star cluster is relatively young. For this one, the age of this star cluster is somewhere around 3 to 8 million years. So if we were looking at an older star cluster, we start with a whole bunch of stars across the main sequence. We start with a whole bunch of stars across the main sequence. If that star cluster is getting older, which are going to be the first stars to begin to die off and begin to turn into giants and supergiants? Well, if these high mass stars have shorter lifetimes, the high mass stars should start going through their stellar evolution more rapidly, turning into giants and supergiants, and eventually dying off. So let's look at this one. So these are all kind of simulated clusters of stars of different ages. If we have that full set of stars, and maybe just the very, very highest mass main sequence stars have turned into a giant or supergiant, this would be a fairly young cluster, around 10 million years old. As time goes on, these higher mass main sequence stars are going to start dying off more and more. So after around 100 million years, all of these very high mass main sequence stars, they've already died off. And some of the main sequence stars right around here, they are just starting to die off. They're starting to move off of the main sequence and turn into giants and supergiants. Again, when we talk about stellar life cycles, we'll go into more detail of how this happens, how a star changes from a main sequence star that has gravitational equilibrium and is fusing hydrogen into helium in its core, and basically how when these stars run out of fuel and start fusing hydrogen outside of their cores or start fusing heavier elements, those stars are going to expand in size and are going to actually become these giant and supergiants. But again, the thing that I want to focus on here is that the first stars to die off are going to be those high mass main sequence stars. As time continues to go on for older clusters, this would be a cluster around 1 billion years old, more of the high mass main sequence stars have died off. We see at this point where we have what's called the main sequence cutoff. If I look at a star cluster and I can see where that main sequence set of stars, where it's just about to be the last one, the next one that's about to leave the main sequence, we can actually use that to identify approximately how old are these star clusters. If I have a single star, just an individual star, it's very, very difficult to identify how old that star is. But if we have one of these star clusters that, again, occur a lot, if we have one of these gravitationally bound star clusters, if I can identify what are the heaviest of the main sequence stars still in that cluster, then we can identify, well, how old is that star cluster? So notice more and more of the stars are dying off. We're even getting a few white dwarfs starting to show up down here. If we were to wait around 10 billion years, more and more of those high mass stars are dying off. And it's just these low mass main sequence stars that have these very, very long lifetimes that are still sticking around. And again, the exact process of how these stars move off the main sequence, start expanding into giants and supergiants, there is some other kind of processes that go along with these giant phases of stellar evolution. We'll talk about those in more detail later. We're also getting more white dwarfs. But again, by looking at these different star clusters, this is another cluster that is a little bit older than the first one we looked at. And you can actually see that these main sequence stars, eventually, we don't get any more of the high mass main sequence stars. Those are moving off of the main sequence branch. So in some of these really large globular clusters, these clusters of stars, some of them can be very, very old. And as they expand into giants, there are other things that can happen. We can get this thing called the horizontal branch of how stars are evolving from giants and supergiants into other semi-stable states. Eventually, they'll turn into white dwarfs. But we can actually detect this by looking at actual star clusters. This graph is pretty similar, a little bit skewed, a little bit kind of rearranged than what we've seen. This is essentially the brightness of the star and a way of measuring the color based on how bright it is in the ultraviolet part of the spectrum and how bright it is in the infrared part of the spectrum. So again, there are different ways of setting this up, but we still get that main sequence, those main sequence stars, and eventually that thing cuts off and we expand into these giants and supergiants. And again, there's can be other motions kind of after that. So again, these clusters, if these main sequence stars did not follow this particular pattern of having short lifetimes for the high mass main sequence stars and longer lifetimes for the low mass main sequence stars, these patterns could look entirely different. We'd still get that weird long main sequence line, maybe with a few gaps out of it, if stars just randomly had different lifetimes. So again, this is a way that we can use star clusters basically as kind of like family photos of how have these different mass stars aged differently if they're all the same kind of age. Now, there's one other thing that we can do with these star clusters. Actually, there's a lot of other things that we can do, but one that we're going to talk about. We can use these star clusters as another way of measuring distances. So earlier on, when we talked about methods of measuring distance, we said we can use this parallax method to say, as the Earth orbits around the sun, relatively nearby stars, we will see a little bit of a shift in their position on the sky. If we can measure that parallax angle, then we can determine what the distance to that star is. The problem is, the further away the stars are, the smaller that parallax angle, and eventually those parallax angles get too small to measure. The best parallax measurements we have are from the Gaia satellite, which is still kind of in the process of finishing off its mission and releasing its last data set. But that Gaia mission, the European Space Agency Gaia mission, has made the most accurate parallax measurements so far. But even those don't really work out past around a distance of 20,000 light years. We can get a little bit further in some cases, but that's kind of approximately the limit. So what if we want to measure the distances to things that are further away than 20,000 light years? Well, if I were to know the apparent brightness of the object and the luminosity of the object, then we can kind of work this equation backwards and figure out the distance. If we rearrange that equation, distance is the square root of luminosity over 4 pi times the brightness. So if I have the luminosity of a star or some kind of celestial object, and I know the apparent brightness, I can work out what the distance is. So let's say I look at one individual star, and let's say it's a type K star. If all I know is that it's a type K star, can I determine what the luminosity is? Well, if it's a type K star, I know on this HR diagram, it's somewhere along this line. But without more information, I don't know if it's a type K main sequence star, or if it's a giant, or if it's a supergiant, and all of those have vastly different luminosities. So if I have just one star and I measure its luminosity, or sorry, if I measure its spectral type, I can't really say for sure what its luminosity is, because I don't know if it's a main sequence star or a giant star or a supergiant. However, suppose I look at a cluster of stars where for that cluster of stars, I make a graph of brightness. So the apparent brightness versus the spectral type, the O, B, A, F, G, K, M. Again, this is almost like our luminosity graph, but we're using brightness instead. If I look at a cluster of stars, I can say that all of these stars are approximately the same distance away. But if I look at this cluster of stars, I might find something like this. If I start drawing dots where I see some of these stars, I might get something that looks kind of like this. Something that has this sort of a shape to it. And it kind of swoops back and does something like that. So let's say I have that particular star cluster. And let's say I pick out a particular type K star. Let's say this one right here. Well, now I know it's a type K star, and what spectral type is it? Well, if it's on this kind of diagonal band, that's got to be a type K main sequence star. And if it's type K main sequence star, I know the luminosity of type K main sequence stars to a reasonable level of accuracy. So if I can identify this pattern of main sequence stars, we have a reference luminosity for identifying what is the luminosity of that star that we're observing. And if I know the luminosity and I know the apparent brightness, I can use that to figure out what is the distance to this particular star cluster. So by using an entire star cluster, if we can look at a star cluster and identify that pattern of main sequence stars, we can use that to say, I know these are main sequence stars. I can look at the spectras of those stars and identify their spectral class. And if I know that it's a main sequence star and what the spectral class is, I can determine the luminosity from that. If I know luminosity and the apparent brightness, I can get the distance. One other thing that we can do, just as a last little comparison, is let's say I look at two star clusters, this blue one, and let's say I have one that's doing something like this. So let me label this one as red, the kind of general pattern that we're getting for this particular star cluster in red. So we have these two star clusters. Based on this data for, let's say, cluster 1 and cluster 2, so blue is going to be cluster 1, red is going to be cluster 2. Can I identify which one is further away, and can I identify which one is older between these two star clusters? For this kind of method, we're not going to worry about actually doing the calculations. We're just going to kind of look at this as a comparison. So try to pause the video for a moment and identify which star cluster is closer to us, or sorry, I think I said which star cluster is further away, and which one is older. So pause the video for a moment and try that. Okay, so let's have a look at these. If we have these two star clusters, we can identify in both cases those main sequence bands. We know that main sequence stars, if we know their spectral type, they'll have a consistent luminosity. So think about it this way. These main sequence stars in these two clusters, which one appear brighter to our eyes for just the main sequence stars? Well, if this is brightness versus spectral type, well, the one that's higher on the brightness scale, cluster 2, it looks like it's going to be brighter to our eyes. Well, if it's brighter, if those main sequence stars are brighter to our eyes, but we know they have the same intrinsic luminosity as the stars in cluster 1, well, if it appears brighter to our eyes, but it's the same luminosity, it must be closer to us. It must be closer by. So object 2 is closer to us. Sorry, cluster 2 is closer to us, and cluster 1 is further away. We can make that comparison. What about the ages of these star clusters? Which one is older? Well, as we talked about before, the stars that die off first are these high mass main sequence stars. And if we compare these two clusters, well, it looks like cluster 1 has had more of its high mass main sequence stars die off than cluster 2 has. So if cluster 1 has had more of its high mass main sequence stars die off, it must be the older cluster. More of the high mass stars have died off. For cluster 2, some of these type A main sequence stars are still kicking around. So this cluster is probably around, maybe 100 million years old, between 10 and 100 million years old, if it still has those type A main sequence stars. Whereas cluster 2, all of those have died out. So this one must be older. This one would probably be around 1 billion years old. So again, these star clusters give us a very, very unique opportunity to test some of these ideas and some of these patterns that we found with the HR diagram and make testable predictions. Again, there's a huge amount of information that both these star clusters and the HR diagram tell us, And again, these star clusters are very common. When we talk about star formation, we're going to see how stars tend to form in these large clusters. But again, it gives us very useful ways of actually testing out these ideas and making sure that we are being scientific in putting each of these ideas to the test.